Welcome to Ælementz, your daily source of insights across finance, science, history, and beyond. Whether you're traveling, tidying, taking a lunchtime stroll, or simply relaxing at home, we're committed to providing new content every day, so join us to grow and learn while living your busy life. Today, we're going to delve into quantum computing, a revolutionary technology that could transform the way we process information and solve complex problems that are currently beyond our reach. What is quantum computing? Quantum computing is a cutting-edge field that uses the principles of quantum mechanics, the laws that govern the behavior of the smallest particles in the universe, like atoms and electrons. In classical computing, the basic unit of information is a bit, which can be either a 0 or a 1, much like a light switch that's either off or on. Quantum computing, however, uses quantum bits, or qubits, which can be both 0 and 1 at the same time due to a property called superposition. Imagine you're trying to find your way out of a complex maze. A classical computer would try each possible path one after the other until it finds the exit, which could take a very long time. A quantum computer, on the other hand, can explore all paths simultaneously, thanks to superposition, potentially finding the exit much faster. This ability to handle many possibilities at once makes quantum computers incredibly powerful for certain tasks. Another key feature is entanglement, where qubits become linked so that the state of one directly affects the state of another, even if they are far apart. This is like having two coins that always land on the same side when flipped, no matter the distance between them. This property allows quantum computers to perform coordinated calculations in ways that classical computers can't. The history of quantum computing. The concept of quantum computing began in the early 1980s. Physicist Richard Feynman suggested that simulating quantum systems with classical computers was extremely difficult and proposed the idea of using quantum mechanics for computation. In 1985, David Deutsch at the University of Oxford developed a theoretical framework for a universal quantum computer, setting the stage for future developments. A significant breakthrough came in 1994 when mathematician Peter Shor devised a quantum algorithm that could factor large numbers much more efficiently than any known classical algorithm. Since modern encryption methods rely on the difficulty of factoring large numbers, Shor's algorithm showed that quantum computers could potentially break current cryptographic codes. This revelation highlighted both the promise and the potential risks of quantum computing. In the following years, researchers made strides in building actual quantum computers. In 2001, IBM scientists used a simple quantum computer to factor the number 15, proving that quantum factoring was possible. Fast forward to 2019, Google announced that its quantum processor, named Sycamore, performed a calculation in 200 seconds that would take a classical supercomputer thousands of years. While this specific calculation wasn't particularly useful, it demonstrated the immense potential of quantum computing. Today, companies like IBM, Google, and Microsoft are heavily investing in quantum computing research. Startups and universities around the world are also contributing to advancements in qubit technology, error correction, and quantum algorithms. Although practical quantum computers are still in development, the progress made so far suggests a future where they could solve complex problems beyond the capability of classical computers. How does quantum computing differ from classical computing? Quantum computing operates on principles entirely different from classical computing. In a classical computer, information is processed using bits that are either 0 or 1, like a light switch that can only be off or on. These bits are manipulated through logical operations to perform tasks. In contrast, quantum computers use qubits, which can be 0, 1, or both at the same time, because of superposition. It's like a spinning coin that represents both heads and tails until it lands. Moreover, qubits can become entangled, meaning the state of one qubit is directly related to the state of another, no matter how far apart they are. This allows quantum computers to perform complex calculations more efficiently. For example, consider searching through a massive database. A classical computer would check each entry one by one, which could take a considerable amount of time. A quantum computer can evaluate multiple entries simultaneously, dramatically speeding up the search process. What are the practical applications of quantum computing? Quantum computing has the potential to revolutionize various fields by solving problems that are currently too complex for classical computers. In medicine, quantum computers could help design new drugs by accurately simulating molecular interactions. For instance, understanding how a new medication binds to proteins in the body involves complex chemistry that classical computers struggle to model. Quantum computers could perform these simulations more efficiently, speeding up drug development and leading to more effective treatments for diseases like Alzheimer's or cancer. In finance, quantum computing could optimize investment portfolios by analyzing numerous market variables at once. Financial markets are influenced by countless factors, and quantum computers could process all this information to identify optimal investment strategies, helping investors maximize returns while minimizing risks. Logistics companies could use quantum computing to optimize delivery routes. For example, a courier service with thousands of deliveries needs to find the most efficient routes for its vehicles. A classical computer might take an impractical amount of time to compute the best routes due to the sheer number of possibilities. A quantum computer could evaluate all possible routes simultaneously, reducing fuel consumption and improving delivery times. In cybersecurity, while quantum computers pose a threat to current encryption methods, they also offer solutions. Quantum encryption techniques like quantum key distribution could make communications virtually unbreakable, enhancing data security for individuals, businesses, and governments. What challenges do quantum computers face? Despite their potential, quantum computers face significant challenges that need to be overcome. One major issue is decoherence. Qubits are extremely sensitive to their environment, and any slight disturbance like vibrations, temperature changes, or electromagnetic fields can cause them to lose their quantum state. Maintaining qubits in a coherent state requires isolating them from all external interference and cooling them to temperatures close to absolute zero, which is technically demanding and expensive. Error correction is another hurdle. Because qubits are so delicate, errors can occur frequently during computations. Developing methods to detect and correct these errors without disturbing the qubits is complex. Scientists are working on quantum error correction codes, but implementing them adds extra qubits and increases the complexity of the system. Scaling up the number of qubits while maintaining control over them is also a significant challenge. It's like trying to keep hundreds of spinning plates balanced on sticks. The more you add, the harder it becomes to manage them all without any wobbling or falling. Will quantum computers replace classical computers? It's unlikely that quantum computers will replace classical computers for everyday tasks. Classical computers are highly efficient for general-purpose computing, such as browsing the internet, writing documents, and running applications. Quantum computers are specialized devices designed to solve specific types of complex problems that are currently unsolvable with classical computers. In the future, we may see quantum computers working alongside classical computers. Quantum computers could handle tasks like complex simulations, optimization problems, and cryptographic analysis, while classical computers manage regular computing needs. This complementary approach would allow us to utilize the strengths of both technologies without replacing the devices we use daily. Quantum entanglement and secure communication. Quantum entanglement has exciting implications for secure communication. Through a method called quantum key distribution, two parties can share encryption keys using entangled particles. Any attempt by an eavesdropper to intercept the key would disturb the quantum state, alerting the parties to the intrusion. This could lead to ultra-secure communication channels. For example, in 2017, China launched the Messier satellite and successfully conducted a secure video call between Beijing and Vienna using quantum encryption, demonstrating the potential for global secure communication networks. The global race for quantum supremacy. Countries around the world are investing heavily in quantum computing research due to its strategic importance. Governments recognize that quantum computing has significant implications for national security, economic growth, and technological leadership. For example, the European Union has launched the Quantum Flagship Initiative, investing €1 billion over 10 years to support quantum research and development. Similarly, the United Kingdom has established a national program to advance quantum technologies, aiming to position itself at the forefront of this revolutionary field. Quantum computing is an exciting frontier that holds the promise of solving problems currently beyond our capabilities. While significant challenges remain, the progress made so far suggests a future where quantum computers contribute to breakthroughs in science, medicine, and technology. What are your thoughts on quantum computing? Do you believe it will revolutionize technology as we know it? Share your thoughts in the comments. Thanks for being here. If you find this helpful, consider subscribing. More content is on the way, and I hope to see you again.